Last week was Cheltenham Science Festival, one of the biggest science events in the UK. I went along to see what was going on and catch up with some of the scientists and presenters who were there. First, I met Greg Foote, a daredevil science presenter, and asked him why he prefers the extreme end of science.
Yeah, so I always tend to use myself as a human guinea pig. I most recently did a series for BBC Three that was asking really interesting questions that people have never really had answered. So could you survive being buried alive? What do humans taste of? That sort of stuff. And I kind of like that visceral aspect. I like being able to experiment on myself and use that as a way to kind of get to the bottom of the science.
This show's all about Everest. What have you been up to there?
Oh, so I had an amazing trip up to Everest Base Camp in April. I trekked all the way up there. It took about 10 days to reach Everest Base Camp. It sits at 5,364 metres above sea level, which is higher than anywhere in the whole of Europe. So it soars over the top of Mont Blanc. I went up to join a group of doctors and scientists called Extreme Everest 2. Scientists and doctors from UCL and from Southampton and from Duke University in America, and they're doing some incredible cutting-edge research. So they're all intensive care unit doctors, and the thing is they are looking for new treatments for their very ill patients back home, but they can't do research on their patients because they're too sick. A factor that's shared by 90% of the people in intensive care units is a lack of oxygen. We say they're hypoxic, right? They're suffering from hypoxia. So what they thought is, we'll take healthy patients up to a place where there's also a lack of oxygen, the Himalayas, where they'll also get hypoxic, and we'll see why one person may cope but somebody else might not. And then they'll track that back to new treatments for their patients.
So what kind of things happen to you when you go hypoxic, when you're somewhere where there's not enough oxygen?
One thing we should say, because some people often get a bit confused about this, there's exactly the same amount of oxygen in the air at altitude, right? There's still 21%. But it's the fact that there is less air because there's less atmospheric pressure. There's essentially less air pushing down on top of you. So that's more spaced apart. So for every breath, you get less air in, so you get less oxygen in. Then you start to hyperventilate because your body's trying to get all of this oxygen in, and your heart starts beating a lot faster and your breathing rate changes as well. So those are the basic physiological things. What's really interesting is when you're hyperventilating, it's great, you're getting oxygen in, but you're also breathing out a load of carbon dioxide. And carbon dioxide is acidic, so it leaves your blood alkaline or alkalotic, and that has a lot of effects on the body. So your rate of acclimatization is how quickly you can get your blood pH back towards where it normally is at.
Do they find that some people do this much more easily and some people find it more difficult?
Exactly that. And you can't predict it. So you might say, hey, this guy's really fit down at sea level. He'll be great up at base camp. There's just no correlation between the various factors that can determine who's going to do well or not do well. And unfortunately, I did not do well. Once I got to about 5,000 metres, I felt pretty horrendous. I felt quite nauseous, very dizzy. I just kind of collapsed in the corner of one of the tea houses we were staying in, just going, oh man, get me home. Yeah, whereas a couple of the guys I was with just flew up, mountain goats, straight up. So you just can't predict it.
And is there any kind of experience thing? So if you've been up mountains lots of times, does that mean you're more likely to be okay with it?
Well, you've touched on something quite deep, actually. So one of the things that does affect how you do at altitude is genetics, and there is a particular gene called the ACE gene. The type of allele of that gene that you have can determine whether you're going to do actually better or not at altitude. That's really interesting, but they actually think it's more than that. They think it could be down to your epigenetics, which is something that you can actually modify during your lifetime and then pass on. And they think that possibly if you've been to altitude, that could modify your epigenetics. So if you go back up again, you're already modified, so you're actually going to do better. So that's something they're really interested in. They were looking in this time. We took some twins up and did lots of genetic studies on those. And we also did a lot of genetic swabs on just the volunteers that were heading up as well.
So does that mean there could be a test that when you say, go to your doctor and say, I'm thinking of going to climb Everest, can you do all the physical checks? I suppose you probably need to show you're fit enough and that sort of thing. Is there a chance that they could do a genetic test then and say, now hang on a minute, you're going to struggle?
Possibly so. Like, that definitely doesn't exist now, but maybe if they do manage to identify those particular markers, they might be able to do so. But of course, as we know, that's not black and white. That's not, oh, that's it, sorry, you may as well not go, dude, you're going to struggle a bit, hey? These things can change, and it's very much nature and nurture as well, isn't it, I guess? So I think if you get the opportunity, take the challenge, whatever happens.
So these doctors up the mountain, have they found any ways of helping people to get more oxygen that might be translatable to their intensive care patients?
Yeah, so what's really interesting is this is a follow-up trip to 2007 when a group of them summited. They went up to the top, 8,848 metres at the top of the world. Pretty amazing. And as they were coming down, they basically stuck a giant syringe into their groin to try to take arterial blood, and they measured how much oxygen there was in there. And the measurement they got was the lowest level of oxygen ever measured in a human ever, including any patient in an intensive care unit. And that made them think, whoa, hang on a minute. This could mean that it's not all about the amount of oxygen that you can get into your body, because this guy's got really, really low oxygen, but he's doing all right. And my oxygen saturations were actually higher than the other guys who were doing a lot better, although I struggled. So they're realising that it's not about how much oxygen you're getting in at the top. It's more about how that oxygen is delivered to the tissues, the muscles, the organs. So it's much more about the delivery, that's one factor, and also the efficiency of how your mitochondria, the power plants as it were in your cells, actually use that oxygen. Some people may have really good delivery, whereas other people may have rubbish delivery. So two people may have the same amount of oxygen getting in, but it's how they actually deliver that to the cells. So if someone's got really rubbish microcirculation, they're going to struggle at altitude, and they're going to struggle with the low levels of oxygen you find in intensive care units as well.
Does this relate at all to athletes training at altitude?
Yeah, it does. So one thing we've actually got for the live show, we've got a hypoxicator, which is what the leading athletes use and they use throughout the Olympics to train. They actually sleep on this most nights. Someone like Mo Farah will sleep in a tent with a tube from a hypoxicator into this tent, and he breathes low oxygen air. So it's essentially like he's sleeping at 3,000 metres or 4,000 metres. And that's because those physiological responses, your body produces more red blood cells. It gets primed to take in much more of that oxygen. So yes, that is why athletes train at altitude, because it has physiological effects on their body to help them get oxygen where they need it in the middle of a race.
Next, I bumped into Professor David Spiegelhalter, Winton Professor for the Public Understanding of Risk at the University of Cambridge. Professor Spiegelhalter has a new book out in which he introduces the idea of micro-lives. So I asked him to tell me a little bit more about what these are.
Well, this is our sort of slightly amusing attempt to try to communicate the effects of chronic risks. These are, everyday habits, our exposures to do with what we eat, what we drink, what we smoke, the exercise we take, maybe our exposures to radiation, all these kind of things are just part of our everyday lives. And what effect does that have on us? And it's not going to kill us straight away. It's not an acute risk in that sense. But by epidemiological studies, you can work out that it will, on average, shorten your life. Not definitely. People might smoke away and live till they're 100, but probably not. It's probably going to, if you smoke, on average, it'll take 9-10 years or so off your life. So that's one way in which you communicate the risk of a habit, is by saying it'll take some years off your life. It's not very effective, really, because people think, oh, well, that's just a couple of years less being old and, grey and dribbly and whatever. And, who wants to be like that? So we do what's called temporal discounting, that we don't take so much notice of what's going to happen a long time in the future. To get around that, we've just got this idea of working out a sort of pro rata effect. So processed meat, sausages, bacon, whatever, there's reasonably good evidence now that if you really have quite a lot of it, 50 grams as a sausage a day or 3 rashers of bacon every day of your life, it's going to, on average, shorten your life by about a year. Processed meat is associated with increased risk of bowel cancer, etc., etc. So that's a year off your life. Well, over an adult life of about 50, 60 years, you could say that's about 50th of your life. Pro rata, that's a week every year, or about half an hour a day. So it's as if eating that sausage or eating that bacon sandwich, as if it's taking half an hour of your life on average. Now, who knows the effect of that sausage on you? I mean, you eat one sausage, there's no way you could say what actually the effect of that sausage is. But if you keep on, with that diet and that habit, then it's as if, on average, that's what it's taking off your life. So we're using that as a sort of metaphor for the effect of daily habits. Adult lifespan of about 55 years or something like that. 55 years or 57 years is 1.5 million hours. So adults, you've got about 1.5 million hours to fritter away during your life. Now, how are you going to spend those 1.5 million hours? You're going to watch, the Eurovision Song Contest. That's sort of 6 of those half hours gone straight away. Bang. So we've called one of these half hours a micro-life, 1/1,000,000th of your life. So every half hour that goes by, it's about 1/1,000,000th of your adult life. Just think about that. So the point is, we get 48 a day. We're ticking them off. That's just how time goes. But actually, by the way we live, we can earn or lose some. We can whip through them a bit quicker than 48 a day. Or we could actually save a few. In a sense, we're slowing our lives down. If we exercise and eat well, don't smoke, drink in moderation, we are slowing down our aging. We are aging more slowly. And people don't want to get older faster, on the whole, apart from maybe sort of teenage girls or something. But I don't want to get older. I think most people say, I don't want to get older faster. And so we're using a metaphor of accelerated aging or slowed aging for the effect of your daily habits. And the microlife is just a way to do that. So we can say that if you exercise, epidemiologically, about the first 20 minutes of exercise each day for someone who otherwise would just be sitting on their backside on the sofa, puts about an hour on their life on average. It's as if it's putting an hour on your life for the first 20 minutes. It's a really good return. We use that quite a lot in the book to make comparisons between eating, drinking, smoking, taking statins, exercise, being exposed to air pollution, etc., etc.
So this is a kind of metaphor to help people understand this idea of overall long-term risk, because as humans, our brains aren't really programmed to understand that sort of thing. As you say, we don't care about things that are going to happen a long time in the future. And this is obviously a problem that you found when trying to communicate the idea of risk. What other problems are there that you found when trying to explain to people what risk really means?
Well, I'm not sure what risk really means myself. So that's the first problem, is I don't know what it means. And nobody else does. I disagree with anybody who says they do. I think humans are amazing things. I mean, they can deal with the massive uncertainties of life. And that's part of being a human. We don't want to know what's going to happen next year. We don't want to know even what we're going to get for Christmas. We like uncertainty. We don't want to know everything. We live with it, and that's part of being human. It's wonderful. So when you try to sort of put numbers on uncertainty, about putting chances on things might happen or what the effect of different behaviours might be, that sort of goes against the grain quite a lot. It's quite a difficult thing for us to absorb, and I think very reasonably. I mean, what do these numbers mean? I don't even know what probability means. The chance of you, living till you're 100 is 5% or whatever. For me, it's probably about 5-10%. For kids nowadays being born, about 1 in 3 is going to reach 100. So what does that mean? You've got a 33% chance of living till 100. It's very difficult to find exactly what that means. So I think probability and the idea of chance and uncertainty and putting numbers on it are really difficult. Very difficult for me, for everybody. The idea of uncertainty is not difficult because we're really used to living with it. None of us knows what's going to happen, and we don't want to. But putting numbers on it is intrinsically extremely difficult because, in fact, I think any numbers you put on, you're sort of inventing anyway.
As well as talks and shows from all sorts of speakers, there were some hands-on activities for people to have a go at on site. I headed over to the Discover Zone to see what I could find. So could you first of all just tell me what this is? So I can see 2 big clear cylinders, and they appear to have a drinks bottle in the bottom of each. What's going on?
So this is our bottle rocket experiment. So what we're doing is we've got these bike pumps here, and as you pump up the bike pumps, all that air is built up in these tubes going around. So the pressure builds up in those tubes. As soon as you hit that buzzer, all the pressure built in those tubes rushes into those rockets there, which is going to fly up and hit the top of those tubes. Whoever gets to the top is the winner.
Okay, so are you guys going to have a go at this? Can you tell me your names?
I'm Will.
I'm Lewis.
And how old are you guys?
13.
Yeah, I'm 13 as well.
Okay, so we're going to get 1 bike pump each, and you're going to have a go at pumping them up, yeah?
Okay, so when I say go, you're going to start pumping as fast as you can. Are you guys ready?
Yeah.
On your marks, get set, go! Start pumping up, building that pressure in the tubes. Keep on going, putting all your work into it.
Is it hard work, guys?
A little bit,
Well done.
yeah.
It starts to get more tiring. As soon as you think you've got enough pressure, hit your buzzer and make those rockets go off.
See, it looks like quite hard work, going a bit red in the face there, but neither of them wants to be the first to give up. Do we think we're there yet?
You ready to hit your buzzers? Okay, hit your buzzers on 3. 1, 2, 3, go! Well done.
Very good. So they both hit the top. I think the left-hand one hit it first. So whose was that? Was that hard work? You look about out of breath now.
Yeah, really hard.
So what's actually going on there? Can you tell me the science behind it?
Yeah, what we're doing is building up the air pressure in those tubes. So as soon as you hit that buzzer there, all the air pressure will rush into these rockets, and the pressure is directly proportional to the force. So as the air rushes into there, it's causing a force She's pushing those rockets up and causing them to go all the way up to the top of these big long tubes.
So what happened when we pressed the buzzer? Why did they suddenly go up?
There's a valve inside these boxes just below the buzzer, so all the pressure is held back by that valve. As soon as you press the buzzer, that valve switches, causing it to be open, allowing all the air that you've built up behind the valve to rush forward through that valve into the rocket, which makes that force shoot it all the way up to the top.
Can you tell me your name?
Andrew.
And what school are you from?
St Joseph's.
So we're standing on the red dot, which is a force sensor, and what that will do is pick up the amount of force that you exert when you want to take off. In the air it will register 0, of course, and then when you land it will show the amount of force that you exert when you land back on the pad. So look at the screen and it will do a countdown, 3, 2, 1, and then it will say jump, and then once you jump to 2, 1, jump.
Okay, so we've got a screen and I can see a picture of this young gentleman jumping, and at the bottom there's a graph. Do you know what that graph's for?
Is it the amount of force I use?
So it's showing the force at takeoff again, and then it's showing the force on landing, and depending on whether the force is over a long period of time, you're getting a nice gentle landing, but if it's a sharp peak, it's showing the pain on the joints.
So what could he do to make that graph look different?
So by using his knees to absorb the impact, he can spread that over a period of time, which will make the force on the joints much lower.
Okay, so can you do it again for me, but this time bend your knees more as you're landing, and we'll see how it looks different.
Oh, that's better, yeah.
So what looks different? I think the second peak in that graph looks a bit smaller, is that right?
It's a little lower because it's spread over a longer period of time. So it's the same area, but it's spread over a longer period of time. So that's showing a minimal force, yeah.
Okay, so first time we had quite a dramatic straight up peak and then straight down again, and this time it's more spread out. And did that jump feel any different?
Yeah, it didn't hurt at all.
Okay, so the first one felt a bit more impact on your knees, but that one was more gentle, yeah?
Yeah.
And the visual feedback enables you to really control that much better than doing it just normally without the feedback.
Can this be used to train people to jump better?
Exactly, and we had a tennis coach come by earlier and he was fascinated by what it could do and how it would, again, could be used to train his tennis students to be able to land or control themselves better so as not to minimise the impact on their joints.
So what have we got going on here? I can see a sort of metal contraption and a plate full of chocolate. Can you tell me what's happening?
I can. So here we're looking at which is the toughest chocolate bar, and we're using something called an impact tester. And at Manchester University we've got a big one of these which you use to test metal, and it tells you how much energy it takes to fracture the chocolate. So we're going to look to try and find which is the toughest chocolate bar. So which one out of the chocolate bars here do you guys think will be the toughest, will be the hardest to break?
So what kind of chocolate bars can you see?
Twix, Dairy Milk, 12, Fudge and Kit Kat.
And what do you think is going to be the hardest to break?
Probably the Kit Kat or the Twix, I think. Yeah.
Okay, so we think the Kit Kats. Should we put the Kit Kat to the test first? So this machine here, the impact tester, you can see it's got a weight here on the end of a pendulum. What's going to happen is we're going to put our chocolate in the machine, we're going to let go of the pendulum, it's going to swing, and it's going to tell us how much energy it took to break that chocolate. And if it takes 100% of the energy, that's really tough. If it takes 0% of the energy, not tough at all. So should we test the Kit Kat and see what happens, yeah? If I put the Kit Kat there, we'll put the dial back up to 100, and then will one of you hold the pendulum for me and just hold it so it's level, and then when you're ready you can let it go. Ready, steady. Yay, brilliant. Can you see here that it fractured the Kit Kat, and what number has the needle moved to on the dial?
20%.
So it took 20% of the energy to break that Kit Kat. So the Kit Kat isn't very tough at all. That biscuit inside it makes it quite weak. Okay, so should we test another one? Which one do you think is going to be tougher than the Kit Kat? Kit Kat was really easy to break, so I think we can find a tougher one here. Which one do you think?
Twix.
Why do you think the Twix might be tougher than the Kit Kat?
Because it's got caramel inside it, so it's going to be harder for it to break.
Brilliant idea. So should we put it to the test and see? Same thing again. Can one of you hold the pendulum for me? We've got it back to 100. Whenever you're ready, you can let the pendulum go.
it hasn't like gone through at all. It's been stuck.
So we can see here that if we take the Twix out and we look inside, you can see that the biscuit's broken, but the caramel layer's held it together, which is exactly what you said before. And what number is the dial pointing to?
100%.
Exactly right. So it took 100% of the energy, and we couldn't even break the Twix all the way through. So the Twix is actually the toughest chocolate bar because of that caramel layer. And that's a bit like in concrete, sometimes they put steel in to make that even tougher, and that's like the Twix. The Twix has that caramel to make it really tough.
So there's a big wall with some flashing red lights on it. What is going on here?
Okay, so this is a network-themed reaction game whereby you've got 60 seconds to hit as many of the lights as you can. It's basically every light that comes on is a cyber attack happening on a network, and it's supposed to symbolise the fast-paced and crazy world of cyber networks, really.
Okay, so we've got some flashing lights, and in a second there'll be one on at a time, and what you have to do is press each light as it comes on and see how quickly you can do it. Does that sound okay?
Yep.
Okay, so here we go. Ready?
Are you ready? Go! Go! Middle one!
And what's the best score you've seen today?
So an actual score is, we've got 76. That's Tom Keach's, was one of the school students on Tuesday.
So 76 means they've got pretty sharp reflexes,
Yeah, that's more than 1 a second. So that's pretty good. 3, 2, 1. 35. That's very respectable for a first go.
How did you find that?
It was difficult and hard work.
You look quite tired, quite out of breath now.
Yep, I am.
So do you think that was, can you imagine that being like a real cyber attack?
Yeah, because it's usually fast and quickly done when they do cyber attacks.
Next, I caught up with Professor Andrea Sella, a chemistry lecturer from UCL, who had a show at the festival all about ice. I asked him what makes ice so special.
Well, the talk is called Strange Ice, and it's really just to bring across to people the importance of ice in our lives, but also the complete paradoxes that ice presents to us. It's interesting that we encounter ice very, very early in our lives. I mean, it's probably around the age of 2 that we first sort of start playing with ice. We start finding ice in our drinks, that kind of thing. And we really enjoy that cool feeling in the mouth. The interesting thing is that the idea that you take a solid and you drop it into its melt and the solid floats is something which is deeply ingrained in our minds. And it becomes, in a sense, our kind of mental paradigm of how solids and liquids behave, even though ice is totally unique in that respect. I can't think of a single other molecular material which behaves in that way. Elements, yes, there's a few examples, but molecular materials, there's nothing that I know of where you get a solid that will float on the melt. So it's quite fun in front of an audience to ham it up slightly and to drop ice into water. And the audience, of course, sort of sit there, and then they start to giggle, and they think, what's this idiot up to? And then what you do is you counter that by A, freezing some petrol or something like that and dropping a petrolberg into some petrol, and suddenly your petrolberg sinks. But it really speaks to the extent to which it is so unusual. We just don't we don't see normal solid and liquid combinations.
So normally the solid of something would be denser because when something solidifies, the atoms inside get closer together so they become denser, so it should sink. Why does ice float?
So ice is very intriguing, and the puzzle of why ice floats has been with us a long time. So once X-rays become available to actually start peering inside of crystals, then immediately people start looking to find out what is the structure of ice. And ice turns out to be a very, very peculiar set of paradoxes. And the first thing is that ice is hexagonal, but the second thing is that the oxygens are very regularly disposed within the structure, and they are linked together through the hydrogens, and the way in which they're arranged produces these open channels. And so ice is relatively an open structure, almost a cage structure, which, when it melts, actually collapses down to give what is a relatively dense liquid. So when you compare water with liquid ammonia, what's intriguing is that it's the water that's anomalous and which is actually rather denser than we would expect. But if we go back to ice, there is then a second strange thing about ice. We normally think about crystals as being highly regular structures, and the oxygens in the ice are very regular, but the hydrogens are not. Now, if you think about the structure, the molecular structure, H2O, each oxygen in ice is connected to two hydrogens with a short bond, but then two others with a long bond. And you can draw ice structures, and all you have to do is flip one molecule round, and that changes all the others, and you can have billions upon billions upon billions of permutations and combinations of this. So ice is this weird paradox between order and disorder, all in the same structure. Very, very peculiar, very unique.
So this is all very interesting, and I like an ice cube in my G&T as much as anyone else, but why does it really matter? Why should we care about the structure of ice and how it works?
Well, I think we need to care an awful lot about ice. And the first thing is that, of course, ice is an incredibly beautiful structure. And one of the things is that by understanding these issues to do with order and disorder, and also sort of peculiar things like what happens on the surface of ice, because this is extremely important in interstellar space, for example, the chemical reactions which happen on the surface of ice, the way in which ice crystals form initially, which can give us a lot of understanding about processes that happen in biological systems as well as in outer space. We can really develop a tremendous understanding of much more than just local ice phenomena. And it's, in my department, it's kind of intriguing that there are, I think, at least 4 people who work on different aspects of the ice story. Some who work on the surface, some who work on computational questions to do with how nucleation starts, and then there are others who actually squeeze ice and compress it and change the temperature. And in that case, the oxygens and the hydrogens rearrange themselves into 15 different possible arrangements. Again, there is no other material that has so many different phases. So ice is this remarkable kaleidoscope, but there's more to it. And I suppose we should ask ourselves, why do we like putting ice in our drinks? Which is, of course, where we first learn about ice.
Well, I like it because it keeps them nice and cold.
Well, absolutely. And the interesting thing is most people will say, because what it does is it brings the temperature down to 0, but it does much more than that. And that is, it actually holds the temperature at 0. So long as you have an ice cube there, your glass stays cold, and the moment the ice is gone, then the temperature rises again. And one of the striking things at the moment is to go and take a look at photographs of Arctic ice. And we have satellite observations going back to 1979 or thereabouts. And then there are memory and recordings and measurements and so on that have been done on ground-based. But you can go and look up websites and take a look at what the extent or the volume of the ice was as far back as 1979 and compare them with what's happening now. And what is absolutely shocking is how much the ice has disappeared from the Arctic. The minimum in the Arctic ice in 2012 was about half of what the minimum was in the 1979 to 2000 period. So really, in those 12 years, we've dropped by an enormous amount. And so I guess the question that I would ask is, are we really prepared for what happens when the ice is gone? Because the ice is an extraordinary reservoir which actually helps to stabilize temperatures. The thing about ice is that over the centuries, the ice has again and again revealed secrets. It has spoken to us in an extraordinary way. And I think it's really important that we listen to the ice.
Finally, I had a chat with Hugh James, science presenter and extreme sports fan, about his show, Extreme Sports in Space, and whether doing them on Earth wasn't extreme enough already.
It's funny because extreme sports in space is a really good way of looking at the different properties that planets have, and their moons as well. You are right that extreme sports here on Earth, if done right, can be quite extreme, although they are quite safe. When you're doing it on other planets, probably not as safe, but definitely extreme nonetheless.
So what kinds of extreme sports could you do, and what would be the best planets to do them on?
Going in from the sun right through to the outer planets, each different planet has a personality. It has different properties that it can offer. For example, Venus, even though it's covered in really, really thick clouds, kind of like it's got a runaway greenhouse effect where it's extreme pressures, extreme temperatures, is still pretty good for extreme sports because it has big volcanoes. We think that every now and then it kind of resurfaces itself. That's one of the theories of why all the rocks on the planet are still quite young. But it also has, even though it's got thick cloud and extreme temperatures, one part of the atmosphere you can still get precipitation. It's kind of a lining across the tops of the mountains, which is really reflective, and it could be some kind of snow, probably lead bismuth snow. So when people say don't eat yellow snow, definitely don't eat lead bismuth snow. But you could ski, snowboard on it, or it could be kind of like sandboarding, but that could be one of the most extreme in the whole solar system, really. And then Europa is a really interesting moon of Jupiter because you might have a water ocean underneath an icy crust. So it could be one of the main contenders for life on other planets. Could be this water underneath there. So scuba diving on Europa would be definitely an extreme sport because you've got all the pressure of the icy crust. Then maybe you get little pockets and little lakes, and then a whole ocean underneath an icy crust with Jupiter to look out on.
So why are these planets and moons so different from one another? What makes them have such different properties?
The reason all the planets are different goes back to when the solar system was first being made, really. As in, the whole solar system was formed through an accretion process. So the sun collapsed from a big cloud of gas, and it created the sun at the centre, and all the heavy elements were pulled further and further in. So we've got all the rocky planets, Mercury, Venus, Earth, obviously, and then Mars after that, all quite rocky in the inner planets. And then you get to the gaseous planets, and then you get to the icy planets after that. So it's a testament to how we were created, really, the structure of the whole solar system and the temperature differences at all of those as well. It makes me think that other solar systems around other stars are going to be just as rich in their differences, really.
And what about moons? What reason is there that some planets have lots of moons and some planets, like Earth, just have one, and other planets that don't have any at all?
Well, Jupiter is massive. It's like the vacuum cleaner for the whole solar system, really. It kind of sucks things in and uses them as little moons. And then you've got Saturn, which again could be the same, but you can't apply that reasoning to the Earth. Our moon is a little bit different. Compared to its host planet, it's one of the biggest in the solar system. And we couldn't live here without the moon. It's really, really important. It's hard to say how important the moon really is, but we still don't really know how it got there. Because it's kind of the same rocks as we get here on Earth. It's more than likely we were hit by something and the moon was flung off after that.
So why is the moon so important for us? I mean, we see it at night, and it maybe gives us a bit of reflected light to see by at night, but it doesn't seem like it's that important on a day-to-day basis.
It is one of the most important parts of the Earth system in general, because without it, we won't have tides going in and out. So through an evolutionary process, where we started off maybe in the sea, we wouldn't have really come out onto the land because you wouldn't have things getting washed up onto the shore. It also helps protect us from asteroids and other kinds of impacts coming in. It used to be a lot closer than it is now. It gets further and further away by, I think it's about an inch per year. So right now, when we get solar eclipses, this is the only time through human history that we will actually get it. Further into the future, they won't get it because the moon will be further away and won't completely cover the sun. But also, as well as being a vacuum cleaner for us, I suppose, it helps stabilise the Earth so it doesn't kind of fall over one way or the other. So it helps us in loads of ways that no one even sees.
So does that mean at some point we're not going to have tides anymore when the moon is too far away to interact?
Well, I think we'll have other things to worry about when the moon gets too far away to interact. But yeah, definitely. When the moon gets that far away, we'll still get the atmosphere creating waves and the likes. But you're right, there won't be any more tides, and we won't have the moon to stabilise us. So flipping over from one end to the next on the poles could be a real possibility. The magnetic field of the Earth is kind of flipped back and forth, but the Earth hasn't. We won't be that stable in the future if we don't have a moon, so there's going to be a lot to worry about.
Do you think there's any chance that you'll actually be able to do any of these extreme sports on any of these planets within your lifetime?
Well, going back to the moon is obviously key for that, because we use most of our energy in getting off the Earth, creating that energy to get out the gravitational field and onto the moon. But to get from there then, that could really be a nice station for us to start to go into Mars and to other planets. But there's lots to overcome. The International Space Station at the moment is doing brilliant research into how we'd cope being in space for that long. because from Moon to Mars is about 9 months, probably a one-way trip to start off with. But we need that. It's one of the reasons why I'm so passionate about extreme sports and adventure and expeditions and the likes, is because nowadays field scientists are the adventurers. They are the expedition leaders. They go to Antarctica and Arctic and down caves and to the most extreme places in the entire Earth, and they will be the people to go to the moon and beyond from there. So field scientists are the next explorers.